So I'm somewhere between physics and chemistry. Don't ask me what, where exactly I am. It depends on the day. Yes. So actually, I'm a physicist, but at some stage I understood that I don't understand enough of molecules, and I decided, I already told it to Shiva, I decided the best way to study molecules or to learn is to become a professor of chemistry, because I'm not going to study chemistry. So it takes too long. Yeah, many years I was interested in the phenomena which are concerned with a single atom or molecule. And then one day I realized that they are rarely alone, these atoms or molecules. And then, indeed, it triggered some other interest in me, namely, what do the other do with the atom or molecule I'm looking at? And I started, or mostly I concentrate on what I call purely electronic processes. Purely electronic does not mean that nuclear dynamics is not relevant. It's very relevant, but it's not needed to understand the process. That's the point, okay? It's very relevant, nuclear dynamics. Now, where is the... I don't find the pointer. Excuse me, 1 second. Okay, I will put it in. Okay. So I'm cabled. It's what? Lower? Then you hear better? Okay, fine. So let's start with the fastest process, decay process in atoms and molecules. When I talk about atoms and molecules, I mean not too heavy ones, because if they become very relativistic, other things become also important. So the doesn't move. So the fastest process is the Auger decay, or many people call it now Auger-Meitner. I will say Auger, but I mean Auger-Meitner, if this is a new name, which makes some sense. Now, here you divide the electronic shell into something which you would call core and valence, and in the valence you can do another division like outer valence and inner valence, which is not relevant at the moment. So if I ionize a core electron, I remove it somehow from the system. This decays very, very fast. It's typically femtosecond. In some favorable cases, it is even sub-femtosecond. And what the decay goes this way, that an electron from the valence falls and closes the hole to minimize, so to say, the energy of the system, and the excess energy is used to kick out an electron. And everybody knows this process at extremely many applications. So now I would like to go to and explain that the Auger decay is actually a local effect. The wavelength of the Auger electron, the de Broglie wavelength, is so short that it doesn't really see the environment. It averages out. So the total rate depends very little on the environment of the system. And since I would like to understand purely electronic processes which are environment affine, it means they are not due to a local decay, so they exist only due to the environment. That's important. And 3 such processes are named here. Let's see, ICD, ETMD, and ISEC. I'll explain later what is what. We'll talk only on the first 2, and Nicola will talk about ISEC tomorrow, as far as I understood. And they have many different manifestations. This is very important. It's not, it always looks the same. You have to discover that this has happened there, so it makes it quite rich. Now, by now, there are more than 400 publications on those systems, and more than 200 or 250 experiments. And there is a bibliography which is collected in our homepage of the Institute, where you can see all the papers which have appeared until now, and divided into theory, experiment, and experiment plus theory. And a recent review has been published mostly done by Till Janke. Okay, so I will, as I said, I will not talk about ISEC. This I will refer for tomorrow. Now, what is ICD? At first, so we looked at what happens if you don't ionize a core, where we know that Auger is the most important and very fast process. It doesn't mean that ICD does not happen after core ionization, but it's not so relevant like that. If you ionize an inner valence, there might be no Auger whatsoever, and then the energy, the excess energy after removing an electron will be taken by the neighbor. So an electron falls in, a outer valence falls into the inner valence hole, and you kick out an outer valence electron. Then you have two ions, because this was after removing an electron, and you have a Coulomb explosion. I will explain that this is not necessarily confined to ions, but the first work was on ions. Maybe even luckily, because it's easier to make an experiment when you have a Coulomb explosion. And it's a very general phenomenon. You might see it. So it was done for hydrogen-bonded clusters, for van der Waals clusters. There are works on quantum dots, quantum wells, and so on. And it's very fast, typically in the femtosecond regime. And it becomes, that's the most important point, faster the more neighbors you have. Okay, I will explain it on an example. It's a source of low energy electrons. They are very slow here, typically between 0 to 10, 15 electron volts, not much more. So this is exactly the range where they are of biological relevance. I will mention it maybe a bit later again. Now, this is a cartoon which I love to take from the first experiment, first coincidence experiment of the Frankfurt group, Till Janke and Reinhard Dörner and their group. And so that's a cartoon taken from their paper. So you have two neon atoms. So the green are the electrons, the valence electrons. The core you don't see, it's somewhere here. So you have the 6 2p electrons and 2 s electrons. So that's outer valence, that's inner valence. You kick out by a photon the inner valence, then an electron from the outer valence falls in. You transfer the energy over quite a distance, and you remove an electron from neighboring neon. Then you have neon plus, and you have a Coulomb explosion. And everything was measured in coincidence, and that's the way you can prove what's going on, because you can calculate with nuclear dynamics in great detail. Okay, maybe I'll come back later for timescales. Now let us see it energetically. So if here I have a neon atom and a neon dimer. Then the internuclear distance in the neodymer is over 3 angstrom. So they just hang around if you like. For the calculation, it's very easy to put them somewhere. But for experiment, it's important that you have a body you can measure it, and a dimer is rather suitable. Okay, so here we have, if you look at the ionized states of neon, so neon plus, you can remove a 2p electron, or you can move a 2s electron. So you can see the energies involved here, but it's not confined to neon. It's rather important in molecules, so the energies will be much smaller. Now, if you go to the neon dimer, no, let me first say, is there an Auger process? No, there is none, because the channel for the Auger process, so double ionization potential, begins here, so something like 12 or more EV, maybe 12, 13 EV are missing, because you need to overcome this energy, and you don't have it in the system. So this is a one-side, so-called one-side state. There is neon plus plus. Now, if you take a dimer, you see on that energy scale, you hardly see any differences. And you have the one-side levels, which are neon 2 plus neon. You see, again, that's a calculation. There is hardly any difference to the atom. But if you look at the two sides, so neon plus, it's here. It's below the energy you have at your disposal when you removed an inner valence electron. Now it can decay by emitting an electron from the neighbor to get to this state with emitting an electron of this energy. So it's typically depends on the nuclear dynamics, but here it's about 2 eV or something like that. Okay, so what I promised to say, I said that it becomes faster if you have more neighbors. Okay, and I think that's the central point of this process. It's totally due to the environment, and the richer the environment is, the faster it becomes. Let's have a look. So neon 3 looks like that. These are the various clusters. Typically, in bigger clusters, you have each neon atom is surrounded like by 12 nearest neighbors. Now, if I ionize here, I remove the 2s electron here, I can transfer the energy to the left and to the right. Okay? So since they hardly talk to each other because they hang around at some distance where you have no chemical bond, it's just a physical van der Waals bond. Now, then it means that the probability will be double from that of a dimer. And since the lifetime is inversely proportional to the width, so this probability, it means that it will be double as fast. So here it will be triple, and so on and so on. And if you get here, you see already that it is a bomb, although it's just rare gases. Okay? And the next shell can also contribute something, but let's forget about it at the moment. Okay, here is a historical calculation of the width. You see the width with the number of neon atom, it goes linearly. Something happens here, which it's not fully clarified yet whether it really goes down up the width more than linear or whether it's a kind of numerical artifact. Now, if you look 1 over the width, you get the lifetime. You see if you have nothing happens in neon atom with a hole in the 2s, it just emits a photon and goes back to the ground state of the ion. It takes about 1 nanosecond to emit a photon. But if I have a neighbor, so here 2 means a dimer, it's about 90 femtoseconds. Okay? So it was measured even in time-resolved experiments. It's something between 100 and a bit more due to the nuclear dynamics, because at larger distance, we'll discuss it later, it is of course slower. Now, if I have 3, it's already below 60, and you go down, and at the end, it's just a few femtoseconds. So it's as fast as the fastest processes we typically know. And I think that's a very relevant point. There are experiments which, like the experiment of the Swedish group around Öval at that time, which shows that in bigger systems, the lifetime becomes just a few femtoseconds in neon. Okay, so that's also historical. I want to give you some overview. And history is important here because after the rare gases, it was important to know, does it happen in reality? I mean, rare gases are, so to say, nice to study, but they are not everyday's life. So water was a big step forward. So our first calculations, which I showed you the cartoon from, was on water. But it took a long time until water was measured. And maybe I should also mention that the first measurement on ICD at all came about 7 years after the predictions. Yeah, and partly because in the beginning I insisted on water, and then I was told, do rare gases, and then indeed, then the measurements started to come. Okay, so I will briefly discuss two measurements which are relevant. One is a dimer. This is a electron-ion coincidence experiment where all particles were measured in coincidence, and you really prove that this is what happens. And then an experiment by Uwe Hergenan and his co-workers from Berlin. So this is a Frankfurt group. I showed you the cartoon about the process before from this paper. Not from this paper, from this group. And here it's bigger clusters, water clusters of about 100 on average. So if you, here you can prove it, and here you can see whether it's consistent, whether it happens in bigger systems. Who knows, maybe it stops for some reason or whatever. You never know in the beginning. So that's the measurements on the dimer, the time of light, like we had today quite a number of those time of light, but this is now time of light, so the coincidence measurements, the kinetic energy release measurement, the electron measurement. This bump here are the photoelectrons, because they chose, so to say, they ionize the 2s with a photon which leads to these photoelectrons. If you take a larger photon energy, this will move out. So then you see, there are such experiments, then you see it goes to about 10. In the bigger clusters, this, for those people who like to study photoelectron spectroscopy, this is the spectrum of the bigger clusters in water, photoelectron spectrum. And you see that ionizing the 2s, so to say, this is that peak, leads to lower energy electrons. Now, there is a clever experiment by Uwe Hergenan in his group, and you also see there electrons which go between 0 and 10. And this is our very, very old calculation, which also goes between 0 and 10. This makes sense. So it peaks at very low energy and goes down quite far. It generates, so ICD generates low energy electrons in water, exactly where the energy range is, where electrons are known to cause DNA strand breaks by dissociative attachment. This was shown by a number of groups. And yeah, so this I just would like to mention. Yes? From one of the oxygen, yeah. Yes, and then the energy relaxation leads to ionization of the other water, and then they fly apart, yes. Okay, so ICD is rather general. I showed you ions because it's also simpler to make the experiment and to realize everything. But whenever the excess energy of a system is sufficient to ionize a neighboring system, it can be a neutral ionized, which I showed you, doubly ionized and so on, it will happen. You have an excess of energy and you can calculate the probabilities that it can happen. Of course, it can be competitive with something which is faster, or in many cases, you don't have anything which can be faster, like in the neon or what I showed you, or also partly in the water. And there are also, but these are experimentally verified. There are also calculation on quantum dots, quantum wells by a number of groups, which is very, very interesting, but there are no experimental realizations yet. Now it can be triggered, it doesn't matter how you excite your initial state, so that's clear that most experiments were done by light, synchrotron, laser, FEL. Then there are nice experiments by electron impact. I gave two examples here. Then there are some by ion impact. I also gave two examples here. So in principle, it doesn't matter how you do the excitation. It must be well defined, else you don't know how to analyze it. Now, there are many manifestations, like I said already in the very introducing words, and surprises. So it can be a competitor to Auger. It means that Auger is very fast, but ICD can be also very fast. If you have many neighbors, so it can really a part go to ICD, a part to Auger, but usually Auger wins if there are not many neighbors. Now, in any case, in an environment after Auger, you will always have ICD, because many states of the dication, trications, which are produced by Auger, are excited and have enough energy to undergo ICD with the neighboring atoms or molecules. No? Now, I will show you one example. So a particularly efficient cascade is created by exciting a core electron. So this is a core excitation. There is some kind of book chapter by Kirill Gockberg on electronic decay cascades in chemical environment. It's a book chapter, it's not a paper. Now, let me go through this slide. If I take a core electron and I excite it, so to say, to a originally empty site or orbital, so to say, like in a big system, it is rather site-specific. Okay, so let's say I excite here, because the energies are also specific to the site. It's different from ionization. If you ionize all, for example, carbon, all carbon atoms will usually be ionized. In a big system, there can be many, so you don't know where you are. Here you know where you are, so it is site-specific. Now there is resonant Auger, which means that, like in Auger, it's more or less confined to the unit where this atom is there. So it's very local. So it's like the normal Auger. An electron from the valence falls in, and then another electron is kicked out. Interestingly, that if this electron, which you excited here, if this is the one to go down, it's called participator Auger, and it's much less efficient. It's only a few percent usually, compared to what is called spectator Auger, where this stays there because the electrons, which are, their wave function is closer to the hole, they undergo this process. The other one hangs around there. So typically this is between 70 and 90. It can be also well over 90. Depends on the system. So this is a process which happens. Now, after this resonant Auger, you see already here, there are two holes here in the valence and this electron. So it's for those who use this nomenclature of many body theory, it's a two-hole, one-particle excitation, which always has a lot of energy. Its energy, this excess energy, is more than enough than needed to ionize anything, even helium, which is the largest ionization potential in nature. So now we have a lot of excess energy, and I see and nothing else here to compete except of photon emission, which takes typically nanoseconds or even more in this case, because it's a spectator somewhere. So this means this is slow compared to the ICD. And then this electron will fall in, compensate one of these two holes, and the excess energy will be used to kick out the electron. And the major point is that it's energy specific and site specific. So you can use it hopefully one day also for medical issues, but people like to discuss it, but I think it's very speculative at the moment. Okay. So this was a theoretical prediction. And then there are experiments. So there are several experiments which I don't want to discuss now. There is a recent work where this is now really utilized with calcium in water, which is not published yet, and several have been published. Okay. Now, a recent surprise is due to the people in this laboratory here. It is growth of molecules. I must say that this is not yet fully understood, but very interesting. Now, if you take a gas phase pyridine monomers under ambient conditions and you illuminate it with a laser, weak laser, it even can be less than 10 to the 6 watts per centimeter square. So this and so you excite the pyridine resonantly, essentially, but you need 3 of such photons to ionize, to get a single pyridine monomer ionized, because its ionization potential is over 9.2 eV. Okay? The field, that's rather weak, so it does not happen for a single pyridine to swallow more than 1. So how come you find cations of the parent pyridine and also up to the size of trimers? Okay, so this, I don't want to go too much into detail. I just want to show some results. So you see in the mass spec, after illuminating this gas with, let's say, 4.66 or 3.49, which is even less. So this is inset here. You see the parent cation, essentially, the parent cation, and you see, however, many with larger masses, okay? This is divided by 10, so that's actually the dominating. So you go to the dimer, trimer, you find the trimer, here is the trimer. You find a lot of fragments of larger. And how can this have happened with photons which don't, where you need 3 ions as a single monomer? You see from the log-log plot of the yield of many of these levels, slope 3, it means it really needs 3 photons. Let's say it is in simple words. So the idea is that it's due to some association in ICD. So for example, you excite 3, you need 3, so at least, so it will be, let's take 3. So you excite 3 by the original photons, which excite resonantly this state, and then let's say 2 go down to their ground state and transfer their excess energy to the third one, which is already excited too, and then it ionizes. Then you associate, you get even a trimer. Maybe a H atom goes away or something. That is what typically happens, which I also showed here, minus H atom. Okay, now this was a surprise, and there are several surprises, at least to me. I am always again surprised that something like that can happen. Now let's talk a little about coherence in ICD. ICD is actually a coherent process, and but where would you see that? Okay. So one possibility to see that is if I go to a cavity. It has not been measured. It's only to explain what I expect. Now, if I have A excited and a B, okay, let's say they are all atoms. It's for coherence much simpler to discuss atoms than molecules because of the nuclear dynamics decoheres a lot, and it becomes more complicated. So if A star has enough excess energy to ionize B, so it goes to A and B plus, and you have the ICD electron, like I showed you several times. And so, but now if we coherently excite several A's, I'll show you examples, it is clear that there will be a strong impact on ICD. So particularly interesting are so-called super radiant state, where you excite several, I mean, you excite only one, but the excitation energy is distributed among several excited atoms. Or this can be done in principle in vacuum, and or polaritons, which are states in the cavity. I'll explain it briefly. In a cavity, the light is quantized. So you have a quantized light like an harmonic oscillator, the electronic Hamiltonian, and of course coupling between the quantized light and the molecule. So this is something to do with a transition dipole of the state we are looking at. Now, then if the coupling is weak, you have a superposition, this is called a polariton, of all, let's say I have capital N atoms, identical atoms, so all atoms and one photon, so to say, of the cavity, plus minus superposition where one of them is excited, it can be the first, the second, the third, all forms such a state. It's a sum, a coherent sum with 0 photons in the cavity. That's a polariton. Okay. So now each of those can undergo ICD, and let's look what happens. Of course, the individual atom decays and it by ICD, and it depends now on the angles. So let's take here A and B. So it depends on the theta and phi, and on the distance, of course. Now, so the cavity, you can calculate it. It's sum of all rates, all divided by r to the 3, which we'll explain a bit later. And it's divided due to the normalization by 2n. Okay. But now, if depends what you do with this sum. You see, if I put n atoms on a ring, it doesn't even, they don't even have to be homogeneously distributed, just on a ring. And this is the polarization of the cavity. Okay? And one atom would, if without cavity, would decay with the rate gamma pi. Okay, the pi, it doesn't matter. Gamma, I want to have another letter, so it's gamma pi. Then all of those, now if they are on a ring, they will add up coherently. So you have n to the square, it's n squared divided by n, it will be n. So you will get a gamma which is n times the original width half because of normalization. Okay, so you can enhance by coherence, you can enhance the process enormously. Okay. Now, for fun, if you just raise the ring from the B is the one which will be ionized. If you raise the ring, you keep everything as it was, you raise the ring, you can come to so-called magic angle, where the 3 cos square of, should be theta, of this angle is 1, then gamma is 0. There is no decay. Okay. And if you tilt the ring, you get some other number. It's a magic angle. So you can really play a lot. Experimentally, it's probably not so simple to do, but that's the advantage of being a theoretician.